Rachel does jumps, each of which is 168 centimeters long. Joel does jumps, each of which is 120, and Mark, each of which is 72. On Monday, Rachel completes 5. Joel and Rachel have the same total distance. Determine the value of n. Well, the distance would basically be the number of jumps times the length of the jump. So in the case of Rachel, it would be 5 times this 168. And they're saying it's equal, same, to Joel. And his would be n times 120. So 120n would be the equation. And then when you solve for this, it's 840 is equal to 120 times n, and therefore n would be 7. On Tuesday, Joel completes R jumps, Mark completes T jumps. Joel and Mark jump the same total distance, and R and T are integers where T is between 11 and 19 inclusive. Determine the values of R and T. So again, 120 times R is going to be equal to 72 times T. So we are basically looking for integer solutions to this. So let's just make a table and see what happens. And the good news is that we are given a set of parameters, so we don't have to try forever. 11, 12, 13, 14, 15, 16, 17, 18, 19. Right? Yeah. Okay, so each of these values of T, just plug it into this guy, and we will get some value of R. And we are obviously looking for values that are both integers. And when you do, this is 6.6, 7.2, 7.8, 8.4, 9.0, 9.6. As you can see, it goes up by 0.6 every time, 10.8, and then finally 11.4. So the only integer solution was that one, where T is 15 and R is 9. On Wednesday, Rachel jumps A jumps, Joel B jumps, and Mark C jumps. Each of A, B, and C is a positive integer. Rachel, Joel, and Mark each jump the same total distance. Determine the minimum possible value of C and explain why this is the minimum. So very similar, but this time we've got 3 variables, 168A, 120B, and 72C. Now, the way to approach this is to break this up into prime factors. So 168 is 2 to the power of 3 times 3 to the power of 1 times 7 to the power of 1, and don't forget about that A. And then 120 is 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 1, and then we got that B. And the 72 is 2 to the power of 3 times 3 to the power of 2 times C. Now, we want all this to be equal, right? So let's take out the stuff that is currently equal, because that is kind of doesn't help us. And I think we can take out a 3 also. That's 3 to the power of 2, so I'm going to make sure I don't miss that. But everything else I'll keep in. So 3 to the power of 1 it becomes. So what I did is I kind of narrowed it down. And when you narrow it down, it makes it a lot easier. So what I believe, and this should be pretty intuitive to you, that the A, in order for all this to be equal, the A has to have a 5 and a 3 in it. Since A is going to have a component of 5 and a 3, let's just make it 5 times 3 for now. Because we're looking at the minimum, right? Yeah, determine minimum. So since we're talking minimum, we'll just keep it at the minimum. B is going to have a component of 7 and 3, and C has to have a 5 and a 7. Now, that means this is going to be minimum values 15, 21, and 35. And therefore, the minimum value for C is 35. Determine a real number, W, for which 1 over W, 1 over 2, 1 over 3, and 1 over 6 is an arithmetic sequence. If it's an arithmetic sequence, that means the difference from there to there is the same as the difference from there to there is the difference from there to there. So basically what that means is that 1 over 3 minus 1 over 2, which would be the difference, would be the same as 1 over 2 minus 1 over W. Got it? So that's basically how you would do that question. So let's do the math here. 1 over 3 minus 1 over 2 is equal to 1 over 2 minus 1 over w. So we've got 2 minus 3 over 6 is equal to, let's see here. Well, let's just keep it in fractions for now. So that means 1 over w would be 1/2, and that's what? Negative 1 over 6? So it would be plus 1 over 6, I believe. Yeah. And then if we add that, that's going to be 4 over 6. So that means w is 6 over 4, which is 3 over 2. So w is 3 over 2. Part B, suppose y, 1, and z is a geometric sequence with y and z both positive. Determine all real numbers for which 1 over y plus 1 x and 1 over z plus 1 is an arithmetic sequence for all such y and z. So something similar. Let's see here. So this is arithmetic. So that from there to there is the same as there to there. So d and d. So same kind of thing here. Yeah, that's arithmetic. Okay, so that means that x, what are they asking for here? Determine all numbers x. Okay, so they're trying to figure out x. So x minus 1 over y plus 1 is the same as 1 over z plus 1 minus x, correct? Yeah. Okay. All right, let's just do this algebra here. So bring the x over, and this will be 1 over z plus 1 plus 1 over y plus 1. And then let's add that fraction. Oh, but we got two variables here. Okay. Yeah, well, we have two variables. Actually, we have three variables, and we want a real number. Okay. We don't want something in terms of y or z. Okay, so this is, I got to come up with something different here. This is the right process, but before I continue, I believe I'm going to have to get y in terms of z or vice versa, and that's where this part comes in. That y, 1, and z is a geometric sequence. So that means that this is a, this is ar, and this is ar squared. That's basically what a geometric sequence is. So that basically means that z over 1 is the same as 1 over y. Yeah. Yeah, so that means, yeah, so z is, either z is 1 over y, or y is 1 over z, whichever one you want to use. Okay, so that's going to help, I believe. Okay, let's go back to the question, 2x, and then this z I'm going to have to substitute, so I'll just substitute this guy. 1 over y plus 1, and this is y plus 1 like that. Okay, this guy here, let me just do it on the side instead of having to write out everything again and again. This is going to be 1 over y plus y over y. So that's going to be 1 over y plus 1 over y. So that's basically y over y plus 1. So that's y over y plus 1 plus 1 over y, 1 plus y. So this is y plus 1 over y plus 1, which is basically 1. So that means x is a half. There we go. So I got a real number. Let me just make that obvious to look like a 2, because sometimes a 2 can look like a z, and then that wouldn't solve the question. So we obtained a real number for x. Suppose that ABCD is a geometric sequence with a 1 over a, 1 over b, and 1 over d is an arithmetic sequence, and each of a, b, c, and d is positive and a does not equal b. Determine all possible values of b over a. So this is a geometric sequence right here, this ABCD stuff. So if that's the case, let me just write it here, A, B, C, and D. If it's geometric, that means this is sort of like A, this is AR, this is AR squared, and this is AR to the power of 3. So that basically means B over A is the same as C over B is the same as D over C. And I'll just call that R as the ratio. And I think that's pretty much the definition of a geometric sequence. Okay, so that takes care of that. Now we've got this guy, which is arithmetic. So 1 over A, 1 over B, and 1 over D. This is arithmetic. So this is the whole thing with the common difference. So that means that 1 over D minus 1 over B is the same as 1 over B minus 1 over A. Yeah. Okay, let me just see here if I set that up properly. I think I did. Okay, so now let's work with this. Let's work with this guy first. I think, well, I'm not really sure where to go with that, so I think this is the only thing I can work with. I'm just trying to think, what should I do here? I think we're gonna, well, let me just first write it out. 1 over B minus 1 over A is 1 over D minus 1 over B. And then what I'm going to do is just write the basic definitions. So if you look at this guy here, B is AR, right? If you just look at these guys, B is equal to AR. So let me just write that in AR. And at least I'll have, I'm attempting to sort of get rid of some variables here. And then D would be, oh, I just use, you know, the basic definitions up there, AR cubed. And then B is AR. Yeah, I think that'll be pretty decent. Yeah, so I immediately narrowed it down to 2 variables. Yeah. Okay, let's work with this now. So we got to get a common denominator, R. So this is 1 minus R over AR. And this is R squared. So this would be 1 minus R squared over AR cubed. And then we can get rid of a lot of stuff here. We can get rid of AR from both sides, I believe. Or I can multiply both sides by R squared and make it look identical. So this would be R squared minus R cubed over AR cubed. And this is the same. And then I can just get rid of the denominators and then just have R squared minus R cubed equals 1 minus R squared. Okay, that's pretty much, you know, the same kind of thing. All right, so now let's put everything on one side. R to the power of 3 minus 2R squared plus 1. Okay, so now I've got to factor this. R minus 1, R squared minus R minus 1. So R equals 1. But that, I think, is not possible because we are told that A does not equal B. Because if R was 1, that means A would be B. So that is not a solution. Not a solution. Okay, that's important to point out. So then we got to concentrate on this guy. And that's a quadratic, so unfortunately we've got to set that equal to 0 and use the quadratic equation because I don't think that factors. So R equals, let's see, minus B plus or minus square root of B squared minus 4A and C all over 2A. And that looks to me like 1 plus or minus root 5. Yeah, over 2. And R, there's something about positive in here. Hold on here. Yeah, all are positive, so that means R's got to be positive. So of these, the only one that's positive, I believe, is the plus 1. Yeah. So what are they asking for again? Determine the values of B over A. So B over A, according to this guy, was just R. So B over A, which is R, is 1 plus root 5 over 2. In the diagram, the circles with centers B and D have radii 1 and R respectively, and are tangent at C. The lines through AD pass through B. The line through A and S is tangent to the circles with centers B and D at P and Q respectively. The line through AT is also tangent to both circles. Line segments ST is perpendicular to AD at C and is tangent to both circles at C. There is a value of R for which AS equals ST equals AT. Determine the value of R. All right, so let me just completely draw this again because otherwise it's going to be very messy. So let me just, attempt to draw it again. It's not going to be very perfect, but that's okay. Oh boy, it's not going to, oh, that's really bad. Let me see if I can even attempt to make it look somewhat, okay, that's pretty decent. Okay, so let me just label this. Okay, so basically what they're saying is they want AS to be equal to ST to be equal to AT. So AS, if I was drawing this line down here, this is S right here, this guy. Let me use a different color here. Let me use red. This is S right here. And this point is T, and this guy down here is A. So they want AS to equal ST to equal AT. So basically what that means is the equilateral triangle. Now, it doesn't look equilateral, sorry about that, but you guys get the point. Now, if it is equilateral, I'll draw it again here to avoid it being messy. It would look something like this, right? If this is A, S, and T. Now we all know that the angles would be 60 degrees. And if I draw a line through it, this would be 30 and 30 because of the symmetry of the diagram, and that line is perpendicular, so that's 90. So it's a 30, 60, 90 triangle. And what are we trying to figure out again? I already forgot. Determine the value of R. Okay, and what is R again? R is the radii of the bigger circle, okay? So R would be the radii of the bigger circle. So if this is the center of that bigger circle right here, R, I guess, would be, well, there's one way of labeling it. This is another way. This is another way, and so on. And that's going to be 90 degrees. All right, so I'm trying to think here. How do I approach this? Well, I think there's a 30, 60, 90 triangle scenario that we would have to approach. Yeah. Okay, so let's do the 30, 60, 90 triangle approach, and then we'll take it from there. So what I'm going to do is going to draw this line right here. That's the radius of the smaller circle, and we were told that was equal to 1, I believe, right? So this triangle right here, this one, that I'll draw it over here just to make it a little bit bigger if I can. That triangle is, well, this was 30, right, from here. So that's a 30, 60, 90 triangle. And we all know that the angles, the ratio of the sides is 2, 1, and root 3. The ratio of the sides of a 30, 60, 90 triangle. But we know in this case that the radius is 1, so this is 1 in terms of its value, its actual value, numerical value. So this means this is 2 and this is root 3. So the distance from here to here, I think I might have to, the distance from there to there is 2. And the distance from there to there is 1. So that whole distance is 3. From there to there is 3. And then this distance is R. So then we can use this big triangle, and I'll draw that over here. So remember, let's recap here. From here to here was 2, and then from here to here is 1, because that's the radius of the smaller circle, and this is R, which I have called the radius of the bigger circle. So this whole thing is 3 plus R. And then from here to here, well, that's R, so this is R. And then these angles are again 90, 30, and 60. So again, we've got a 30, 60, 90 triangle, and the ratio is 2, 1, and root 3, and now we can easily use the ratio to figure out R. R over 3 plus R would be the same as 1 over 2, I believe. And if we solve for this, we get 2R is equal to 3 plus R, and therefore R would be equal to 3. So 3 is the answer to this question. Part B, there's a value of R for which dq is equal to qp. Determine the value of R. So again, let me attempt to draw that diagram again. So let's see here. Okay, and now we've got to draw. That's pretty decent right there. Okay, So let's label this as best as we can. And let me just put in the tangents and all that. So how much do I have to label? Let me just label the bare minimum. PQ, let's see here, they call this B, I believe, yeah, it was called B, I was right. And then this was D, and I think for now that's pretty decent. So they're saying that DQ is equal to QP. Okay, I can see both of those on there. And they're saying find the value of R. And R is the same as before, right? R is the radius of the large circle. So that's R, and the radius of the small circle was 1. Okay, so the key to this question is to draw a parallel line like that. So this line is parallel to PQ. Got it? So that means that if this was 1, right? That's the radius. Then that means that this is also 1. So because those lines are parallel, then that means that the distance would be the same. So this distance, which I will put it in green, that distance there, would be R minus 1. So that distance would be R, the radius, minus that 1. Okay? And then because this was 90 degrees, this is 90 degrees. And then now we can concentrate on this triangle right here. This, let me see if I can highlight it in a different color so you can see what I'm talking about. This triangle right here, that triangle that I just wrote in yellow. So let me draw that triangle here, make it a little bit bigger. So that's a right angle. This is R minus 1. This side right here, this side, that side, is the same as PQ. If you notice, because those lines are the same length, so that is the same as PQ, which is the same as DQ, according to the question, and DQ is R. Okay, and then this side right here, the hypotenuse, I guess, is R plus 1. So there you go. There is very quickly a setup for a Pythagorean relationship, and then we can just do that really easily. So it'd be R squared plus R minus 1 squared is equal to R plus 1 squared. So hopefully that will give us something. So R squared minus 2R plus 1, R squared plus 2R plus 1. Let's see here. That goes, that goes, that goes, that goes. So R squared minus 4R is equal to 0. So R and R minus 4. So R is equal to 4, since R obviously cannot be 0. And that solves the question. A third circle with center O passes through A, S, and T and intersects the circle with center D at points V and W. There's a value of R for which OV is perpendicular to DV. Determine this value of R. So here is a diagram that illustrates this whole, opening stem, hopefully. And what we are trying to find is find R such that, that's the symbol for such that, OV is perpendicular to DV. Okay, so let's start here. I think this is going to be a little time consuming, but it should be okay. We're going to have to look at a lot of triangular similarities. And the first one is the triangle SBP. It's similar to triangle DSQ. And therefore, if that is the case, then the ratio would be the same of the sides. So SP over BP would be the same as DQ over SQ. And if we substitute as best as we can, BP is 1, DQ was R, and SQ, well, SQ, do we know anything about SQ? SQ is the same as SP, I believe. Yeah. So that's SQ. So that means SP squared would be equal to R. And therefore SP would be root R. Okay. So that means that SQ, which is equal to SP, which is also equal to SC, is equal to root r. All right, so that's one step. Now let's look at another set of triangles, APB. That's similar to triangle AQD. So that means AB over BP is equal to AD over DQ. So that means we have AB over 1 is equal to AB plus BD, and DQ is R. So that means AB is equal to AB plus 1 plus 1 plus R over R, and then solving this, you'll get AB is equal to R plus 1 over R minus 1. And therefore, AC would be equal to, which is AB over plus 1, would be equal to 2R over R minus 1. All right, so we have some progress here. Now let's look at this diagram again. If we look at this diagram, hopefully we can now label the radius. And what are we really looking for? Solve for the value of r, the small r. So this third circle that they're talking about, we'll let that third circle have a radius. I'll just call it big R. So the third circle, the one that has the center O. Center O. And then if you notice, in that third circle, look at a triangle OSC. In triangle OSC, you will see a Pythagorean relationship where OS is the hypotenuse, and the other legs are OC and SC. So that's what I will work on now. So OS, according to my labeling, is R squared, and that's going to be AC minus AO. Let me just keep that diagram in the frame so you can see. All squared. And then SC, we'll just leave that SC for now. And then R squared, therefore AC minus AO, and AO is also R. All squared plus SC squared. And when I expand this, I will have AC all squared minus 2 times R times AC plus R squared plus SC squared. Okay, so now let's see if I collect like terms. I'll get 2 times R times AC. The R squareds go, and we just have AC squared plus SC squared. Okay, and then if I divide through by AC, or 2AC, I can just have R and then AC over 2 plus SC squared over 2AC. And then now I can substitute. So R, AC I believe is right here, right? That was AC. So that was 2R over R minus 1. And I've got to put a 2 because of this guy. So I'll put the 1/2 out front like that. And then SC, I believe I did that somewhere here. Oh, here it is. SC is root R. So that SC squared, therefore, would be R. Correct? Yeah. And then 2AC, well, then AC is right here, so it's just a flip. So it would be 4R over R minus 1. Yeah. So then where R would be R over R minus 1. And when you invert and multiply this guy, it would be R minus 1 over times 4 times R over 1. So therefore, if I'm doing this correctly, this would be R over R minus 1 plus R minus 1 over 4. That's pretty good progress. And then now we have to look at one final triangle, and that one final triangle is triangle OVD. So let's go back to the diagram. OVD, OVD, that guy right there. You can see right there, OVD, that one. And in that triangle, we have a relationship, a Pythagorean relationship, where OD is the hypotenuse and OV and VD are the legs. So let's go back. So that would mean we've got OV squared plus VD squared is equal to OD squared. Now OV, if you look at that diagram, is really R, and VD is the small r, and OD is OC plus CD. And then this is R squared plus small r squared. And then we have to break this up a little bit more. This is AC minus AO plus CD. And then r squared plus small r squared. And then AC, remember, we had that. And then AO is R, and then CD was R. So now we've got this big, long algebra to do. That is the big, long algebra. You can, I'm sure, do it on your own. So this is what I wrote right here. And we simplify it down to this guy. And then remember, R, I had figured out was this. So once you get down to there, this 2R, you substitute our finding, and then we get this guy. So let me blow that up here. So let me just explain this. So I had come to this point, right? And that's what this is. So you simplify it down to this guy, and then you substitute this R, which is what I had figured out up here. And when you substitute it, you get this big long thing. And then again, we have to simplify and you know, collect like terms and all that. And when you do, you get this, and then finally you get to this. So this is the end result of that monstrosity to try to figure out what is R. And then R cannot be 1, so R equals 1 is not a solution because it represents the radius. So then we got to look at that. And that means r squared minus 4r minus 1 is 0. And when you do a quadratic, which I am sure you can do, you will find that r is equal to 2 plus root 5.